The effect of a complex agonist and antagonist resistance training protocol on volume, load, power output, electromyographic responses, and efficiency. School of Human Movement and Sport Science, University of Ballarat, Victoria, Australia, Department of Physiotherapy, Faculty of Health Sciences, University of Sydney, New South Wales, Australia, and School of Human Kinetics and Recreation, Memorial University of Newfoundland, St. John's, Newfoundland, Canada. Abstract. The effect of a complex agonist and antagonist resistance training protocol on volume, load, and power output, electromyographic responses, and efficiency. Journal Strength and Conditioning Research 24/7, 1782 to 1789, 2010. The objective of the study was to investigate the acute effects of performing traditional set TS versus complex set CS agonist-antagonist training over 3 consecutive sets on bench press throw, BPT, throw height, TH, peak velocity, PV, peak power, PP, bench pull, volume load, VL, and electromyographic EMG activity. 18 trained men performed 2 testing protocols, TS comprising 3 sets of B pull followed by 3 sets of BPT, performed by approximately 20 minutes, or CS comprising 3 sets of both B pull and BPT, performed in an alternating manner in approximately 10 minutes. Throw height, PV, PP, and EMG activity were not different within or between the 2 conditions. Bench pull, VL, decreased significantly from set 1 to set 2 and 3 under both conditions. Decreases from set 1 to set 2, where 14.55 plus or minus 26.11 and 9.07 plus or minus 13.89%, and from set 1 to set 3, where 16.87 plus or minus 29.90 and 14.7 plus or minus 18.37% under CS and TS respectively. There was no difference in VL per set or session between the conditions, although there was no augmentation of the power measures. CS was determined to have approximately twice the efficiency output over time as compared to TS. Efficiency calculations for VL, TH, PV, and PP are 103.47 kilograms a minute, 26.25 cms per minute, 1.98 m per second per minute, 890.39 watts per minute under CS, and 54.71 kilograms per minute, 13.02 centimeters per minute, 0.99 meters per second per minute, 459.28 watts per minute under TS. Comparison of EMG activity between the protocols suggests that the level of neuromuscular fatigue did not differ under the 2 conditions. Complex set training would appear to be an effective method of exercise with respect to efficiency and the maintenance of TH, PV, PP, and VL. Introduction. Complex training commonly involves a coupling of heavy resistance training exercise with a biomechanically similar plyometric exercise performed in an alternating manner. A less common complex training design pairs biomechanical dissimilar exercise with targeting agonist and antagonist muscle groups. For the purpose of this research, agonist-antagonist complex set CS training refers to the coupling of a heavy traditional training set, weight training, e.g. bench pull, beam pull, with a ballistic, e.g. bench row, BPT, exercise targeting upper body muscle groups performed coincidentally. Agonist-antagonist exercises are commonly performed over the repeated trials in an alternating manner with rest intervals, RIs, between each set. Resistance training is an effective method for developing muscular strength and power. It has been associated with improved health and decrease in the risk of chronic disease and disability. Resistance training schemes able to develop strength and power in a time-efficient manner would be beneficial to athletes and the general population. Agonist-antagonist complex training may be one such training modality. It is possible that by alternating agonist and antagonist exercises, the density of work performed could increase. That is, more work could be performed per unit of time. Furthermore, it is possible that gains in efficiency are not at the expense of efficacy. Resistance training protocols that save time without compromising efficacy or increase efficiency could be advantageous to athletes and the general population. Peer-reviewed research into the effects of agonist and antagonist complex training is limited, but has been suggested that this type of training results in acute performance enhancement. Baker and Newton observed an augmentation in power output in the BPT when preceded 3 minutes by a set of B-pull compared to power output achieved in a set of BPT with no intervention. They suggested that antagonist preloading may alter, i.e. shorten the antagonist braking phase, triphasic electromyographic EMG activity during subsequent agonist activity. However, the researchers did not incorporate a mechanistic evaluation, i.e. EMG, into the research. Performance enhancement after antagonist loading has been documented in a single set study. However, CS commonly involves the execution of repeated sets. The second CS also begins with the antagonist loading, as do all subsequent sets. Research involving multiple set studies is necessary to draw conclusions as to the likely efficacy of CS as a training method for developing power. Research investigating complex training as CS has focused primarily on performance enhancement of the second phase power activity of the pair. This only represents half of the training protocol. To date, there has been no studies that have examined the first phase of the complex pair. Research studies have commonly viewed the first phase as the intervention. However, this phase should not be viewed solely as the means to augment performance of the subsequent power phase, but also as an instrument to develop the targeted musculature. For example, if BPT is preceded by B-pole should be seen not only as a means of augmenting performance of BPT, but also as means of developing the musculature involved in the B-pole. Research investigating the first phase of CS is necessary to draw conclusions as to the efficacy of CS as a method of developing strength. Although research into complex training has been undertaken primarily with the intent of augmenting performance of the power activity second phase, it has been suggested that whether performance enhancement is observed or not, complex training may be in a time-efficient method of developing strength and power. To date, there has been no studies reported to have compared CS or to other methods of developing strength and power. Research comparing CS to other training modalities should perform efficiency calculations for both phases of the CS to provide support for the hypothesis that CS is a time-efficient method of developing strength and power. Performance enhancement after loading has been demonstrated in a single CS to date. However, there have been no studies reported that have examined the mechanism underlying or responses to CS in which the agonist-antagonist pairing of high resistance isotonic and ballistic exercises are investigated over consecutive sets. It is possible that this method of training could be efficacious and time-efficient method for developing strength and power. The purpose of the study was to investigate the effect of agonist-antagonist complex training on B-pole, BPT, performance, and EMG activity over 3 consecutive sets to compare those effects to a traditional training modality in terms of effectiveness and efficacy. Methods. Experimental approach to the problem. A within-subject randomization counterbalance design was used to investigate the effects of altering agonist and antagonist exercises on BPT and B-pole performance and to determine whether significant differences in BPT throw height, TH, peak velocity, PV, peak power, PP, and B-pole volume load, VL, load times repetitions, existed between CS and a traditional set, TS, training protocols over 3 sets. Because of the familiarity of movement and the relative widespread use as a means of develop strength and power, B-pole and BPT were chosen as the pulling and pushing exercises respectively. Volume load was chosen because of its widespread use as an indicator of work performed over an entire set or session. The 3 power measures, TH, PV, and PP, are widely used and accepted as variables relating to explosive force production capabilities. The TS protocol was designed to reflect the much practiced resistance training scheme of targeting one muscle group via multiple sets before targeting another muscle group. The CS protocol was designed to stress the same musculature as that stressed under the TS condition, but in less time. Subjects: 18 trained men with at least 1 year's training experience with pushing and pulling resistance exercises volunteered to participate in the study. Participants were generally collegiate athletes, predominantly basketball and rugby players. With several years training experience, and testing occurred during the off-season, the months of May and June. All participants had experience with the CS type of training. The participants' descriptive data are displayed in Table 1. The study was approved by the University of Human Research Ethics Committee. Before the investigation, all subjects were briefed on the testing protocol, experimental risks, equipment, and the nature of the study before signing an informed consent document. All participants were asked to refrain from any upper body training for the 48 hours before each training session. Procedures: 40% of bench press 1RM was prescribed for all sets of BPT 4 throws in both protocols, as loads of 30 to 60% of bench press 1RM and repetitions of 3 to 5 have been suggested to achieve maximum power output. A 4M was prescribed for B-pole for all sets in both protocols and was performed to failure, which was considered to have been reached when another repetition using proper technique could not be performed. A 4M was chosen because high-intensity loads have been recommended for strength development. The total time required to complete the training sessions and the order in which the exercises were performed differed between the two protocols. Specifically, the PS protocol required approximately half of the time to complete as compared with the TS protocol. To assist in the explanation of any observed differences in the THPV and PP, VL, EMG responses of four muscles, pectoris major, anterior deltoid, latissimus dorsi, and trapezius were monitored in every set of both exercises. Specifically, mean amplitude of the root mean square, RMS, and the median frequency, MDF, were collected because fatigue-induced changes in these signals can provide an indication of general motor unit activation and signal frequency, respectively. Throw height, PM, PV, meters per second, and PP, watts, were calculated using a position transducer, PT5A linear position transducer, fitness technology, Adelaide, Australia. The system comprises a cable extension, potentiometer, distance transducer, USB data collected interface, and custom software ballistic measurement system, fitness technology, to accurately measure the vertical movement of the bar. Bench pull VL was measured during all sets of both protocols by multiplying the load by the number of correct repetitions achieved. USB data collected interface and custom software ballistic movement systems, fitness technology to accurately measure the vertical movement of the bar. Bench pull VL was measured during all sets of both protocols by multiplying the load and the number of correct repetitions achieved. Before the commencement of the testing sessions, a reliability study involving the 10 of the subjects who later participated in the study determined the test-retest separated by 1 week interclass correlation coefficients, ICCs, and percent total error, percent TE. Participants underwent 2 familiarization sessions to determine their 4RM for the B-pull, 1RM for the bench press, and to be instructed on the exercise technique. To determine 1RM bench press, participants performed a set of 5 to 10 repetitions using 40 to 60% of the expected maximum, followed by 1 minute later by a set of 3 to 5 repetitions using 60 to 80% of the expected maximum, followed by 1 minute later by a set of 3 to 5 repetitions using 60 to 80% of expected maximum. After a 2-minute RI, 1RM attempts were made with approximately 2-minute RIs between attempts. If an attempt was successful using the correct technique, further attempts were made using increasing increments of weight. To determine 4RM B-pull, participants followed a similar protocol that is described for determining 1RM bench press, but loads of 30 to 50 and 50 to 70% were implemented in place of 40 to 60 and 60 to 80% respectively. The last successful attempt was recorded as the participant's 1RM or 4RM in the lift. This procedure was adopted from Stone and O'Brien. With one change, rather than 1 minute RIs between attempts, 2-minute RIs were used to better ensure recovery between attempts. The familiarization sessions were performed so that the second session was conducted 1 week before the first training session, which was performed 1 week before the second testing session. All testing was performed at the same time of day, and the standardized warm-up specific to the testing protocol was performed in all sessions. Before testing, participants performed progressive submaximal exercise. Specifically, participants performed 3 sets of 4 repetitions of B-pull at 60, 80, and 90% of 4RM calculated from the previously determined 4RM, and 3 sets of 4 throws of BPT using 40% of 1RM calculated from the previously determined 1RM at self-determined 50, 75, and 100% of maximum effort. The 4-minute RA was provided between like exercises. Before the TS testing session, the warm-up sets were executed in a successive manner. That is, 3 sets of first exercise followed by 3 sets of the second exercise, whereas before the CS testing session, the warm-up sets were performed in an alternating manner. When performing BPT, warm-up and testing, participants lay supine on a flat bench in a Smith machine that allowed the bar to move only in the vertical plane. Participants' feet were flat on the floor, and head and shoulders and buttocks were flat to the bench. The starting position of the bar was touching the chest at the nipples. Participants were instructed to attempt to throw the bar in the vertical plane as high as possible, releasing the bar at elbow extension. The B-pull tests were performed on an adjustable high bench, Apex B45 adjustable flat bench positioned on step 1005 platforms. Participants were instructed to lie prone on the bench and grasp the Olympic bar placed on the floor with a pronated grip. The bench was adjusted so the participant's arms were straight in that position. The repetition was deemed to have been completed by moving the bar from the floor until it touched the bottom of the bench. Between repetitions, the bar was motionless on the floor for 1 to 2 seconds. Participants were instructed to keep their head, upper body, and legs flat to the bench. Hand placement and tempo was self-determined for both exercises, and an attempt was made to maintain consistency within participant during and between testing sessions. Participants were permitted to hydrate using water during all testing sessions. Electromyographic data were collected using surface electrodes, Delsey's DE 2.1 sensors, Boston, Massachusetts, USA, with an inter-electrode distance of 1 centimeter using an active differential preamplified configuration, Delsey DE 2.1. These electrodes were connected to an analog to digital converter, Bagnoli Manometer 3 wireless systems, Delsey's Incorporated, and acquired with the assistance of a proprietary software, EMG Works Acquisition 3.5 Delsey's Incorporated. Electromyographic signals were amplified by 1000 with a frequency band pass of 20 to 450 hertz, common mode rejection ratio of 92 dB, and recorded at 1000 hertz, Bagnoli Manometer 3 wireless systems, Delsey Incorporated. The mean amplitude of the RMS and MDF analysis was performed using custom-written software, National Institute Lab View 8, Austin, Texas, USA. Data were collected throughout the entire set for all sets of both BPOL and BPT electromyographic data collected from the entire and concentric and eccentric first contraction were compared to the EMG data of the entire final contraction. The EMG signal was acquired from the pectoris major, anterior deltoid, latissimus dorsi, and trapezius muscles located on the right side of each participant using surface electrode within an inter-electrode distance of 1 centimeter. Pectoris major electrode was placed midpoint between the acromion and the xiphoid process. The anterior deltoid electrode was placed in the midbelly 3 to 4 centimeters beneath the anterior margin of the acromion process. The latissimus dorsi electrode was placed lateral to the inferior angle of the scapula. The trapezius electrode was placed midway between the scapula spine and spinous process of the same level. A ground electrode, flexible 1 centimeter disposable AGCL surface EMG electrode, Thought Technologies Limited, Montreal, PQ, Canada, was placed on the right elbow before electrode placement, and the area of the skin was thoroughly prepared with abrasive paper and isopropyl alkyl swabs to improve conductivity of the EMG signal. Traditional set protocol. Before testing, participants performed a standardized warm-up. Testing commenced after a 4-minute RI. 3 sets of EPOL were followed by 3 sets of EPT with a 4-minute RI between each set. All sets of EPOL were performed to failure using previously determined 4RM load. The load and number of correct repetitions completed were recorded for each set. All sets of BPT involved 4 maximal throws. The testing session took approximately 20 minutes to complete. Complex set protocol. Before testing, participants performed the standardized warm-up. Testing procedures similar to those used in the TS protocol were implemented. However, the 3 sets of EPOL were performed in an alternating manner with the 3 sets of BPT, although the RI between like sets was 4 minutes. The RIs between work performed were less. At the midpoint, and the RI between like sets and other exercises, i.e. antagonistic, was executed. The RI between work performed was approximately 2 minutes. Therefore, the testing sessions was completed in approximately 10 minutes. Under both conditions, during the RI between sets, participants engaged in passive rest. Verbal encouragement was given throughout the testing sessions under both conditions. Statistical analysis. The reliability study determined ICCs on the percent T for set and session VO over 3 sets for B4 range between 0.91 to 6.3% and 0.97 to 12.3%. Paired sample T-test revealed no significant P less than or equal to 0.01 differences between the 2 testing occasions. Intraclass correlation coefficient and the percent TE for THPV and PP over 3 sets for BPT ranged between 0.89 4.2% and 0.98 4.5%. Paired sample T-test revealed no significant P is less than 0.01 difference between the 2 testing occasions. The test-retest ICC for the EMG measured for the 4 monitored muscles ranged between 0.83 and 0.96. The set and sessions totals of the THPV, NPV, and BPT and VL for BPOL were calculated in both testing protocols. These data were analyzed using a 2-way analysis of variance, ANOVA 2x3, with repeated measures and paired t-tests to determine whether they were significant main effects or interactions for the type of training, TS and CS, and the sets 1 to 3 analysis the data to determine if any significant differences existed between the 2 testing protocols was performed to investigate the influence of CS on the maintenance of THPV, PP, and VL. Electromyographic data, RMS, and MDF were gathered for the first and last repetition of each set. Electromyographic data was analyzed using the 3-way ANOVA 2x3x2 with repeated measures to determine whether they were significant main effects or interactions for the type of training, CS and PS. The sets 1 to 3 and the repetitions, first repetition and last repetition, efficiency, VL divided by time, TH divided by time, PV divided by time, and PP divided by time. Calculations were also made. The level of statistical significance was set at P equals less than 0.05 for all tests, with the exception of the 3-way ANOVA comparing the EMG to CS to TS within each condition. which was adjusted using the von Ferroni set at p is less than or equal to 0.901, while statistical tests use SPSS version 16. Effect size calculations were performed on measures of TH, PD, PD, and BL to address the magnitude of the response. Major finding of the study is that all the performance and mechanism measured were similar under CS as compared to TS, indicating greater time efficiency under CS. There were no differences in the set of sessions totals for BPT, TH, PV, and PP within or across the two conditions. Bench pull BL decreased significantly from set 1 to set 2 and from set 1 to set 3 in the CS and TS conditions. P is less than 0.05. With percent changes shown in Table 2, there were no differences in set or session B pull BL different between the two occasions. Bench pull BL and BPT, TH, PV, and PP data were effect size are shown in Table 3. Complex set was determined to be more efficient. Efficiency calculations are shown in Table 4. There was no EMG activity, main effect differences, or interactions. Discussion. Complex set training has been prescribed by practitioners as a means to developing strength and power. It has been suggested that this type of training results in acute performance enhancement. In the present study, augmentation of the performance measures was not observed. However, BPT, TH, PV, PP, and BL were not different per set or for the session under the CS and TS conditions. Efficiency calculations determined CS training to have approximately twice the efficiency as compared to TS training. These findings support the hypothesis that CS training allows for enhanced efficiency. Comparison of EMG data suggests that neuromuscular fatigue is no greater in the CS than the TS protocol. Although participants in the current study were trained men and predominantly college athletes, it is possible that these findings might apply to other samples or populations, e.g. different age, gender, sport background, or training history. It is perhaps not surprising that changes in EMG signal were not observed during sets of BPT. The experimental design in the present study, 3 sets of 4 throws within a 4-minute RI between similar biomechanical work, was intended to allow participants to perform BPT in a non-fatigued state. The absence of significant changes in the EMG signal during sets of the B-pole exercise may have been influenced by the fiber type composition of the monitored muscles and the relative involvement of the muscles in the exercise. Among the 4 monitored muscles in the present study, the latissimus dorsi has the highest percent of type 1 fatigue-resistant fibers, and as such is likely the most fatigue-resistant. The latissimus dorsi likely plays a major role in the B-pole exercise. It is also possible that the 4M B-pole was not of sufficient duration to induce significant changes in EMG activity. Bem and St. Pierre observed relatively little decrease in muscular activation as reflected in the EMG signal and suggested short-term contractions, e.g. 4M, may not result in significant changes in EMG activity as compared with longer duration contractions. Coactivation refers to the concurrent activation of agonist and antagonist muscles, a triplastic pattern of EMG activity whereby a large burst of agonist activity is followed by a shorter breaking burst from the antagonistic musculature, and finally a second agonist burst has been suggested during rapid or ballistic contractions. The performance of a movement may be partially contingent on the net effect of this activity. Baker and Newton suggested that augmentation of BPT performance after loading of the antagonist musculature via a set of aballistic B-poles may have been the result of an alteration in the triplastic pattern. Specifically, the researchers hypothesized that the B-pole altered the timing of the antagonist braking activity. The subsequent 3-minute post-intervention BPT. They postulated that a shorter braking phase from the antagonistic would allow for a longer initial burst from the agonist and thereby allow for the increase in the performance measure. Augmentation of BPT performance was not observed in the present study. This is perhaps because of the implementation of a non-ballistic intervention, 4M B-pole, performed for low repetitions. Tendency to decrease from sets 1 to 3 in the present study as compared with the intervention used by Baker and Newton. Of aballistic B-poles, it is also possible, although perhaps unlikely, that performance was enhanced to a similar extent in all 3 sets of CS BPT in the present study. This would not have been observed as a set of BPT without an intervention, e.g. before the first set of B-pole was not performed. However, the 3 sets of BPT performed under the CS condition were not only similar to one another, but also similar to the 3 sets of BPT performed under the TS condition. That is, if some augmentation occurred repeatedly and to the same extent over the 3 sets under the CS condition, it must have also occurred under the TS condition. It would seem unlikely that a similar level of augmentation occurred before each set of BPT under both conditions, as a result of the cumulative effects of the varying exercise performed before that set. Rather, it would seem more likely that there was no augmentation in performance. It has been suggested that stored elastic strain energy and the stretch reflex may play a role, i.e. enhance agonist performance in movements involving antagonist loading immediately before the agonist activity. However, because of the prolonged RI, i.e. time between antagonist and agonist exercises, and the combination of non-ballistic and ballistic movements, figure 1, used in the present study, and the subsequent results stored elastic strain energy and the stretch reflex were not considered a factor. Although BPT performance was not enhanced, all three measures of power, TH, PV, and PB, were maintained throughout all sets and were similar in both protocols. Fiber type composition and the musculature primarily involved in the pressing as compared to pulling exercises suggest that maintenance of performing measures would be less likely in pressing as compared to pulling activities. This is not observed in the present study. This can perhaps be explained by the nature of the pressing activity, i.e. BPT, in the present study. Unlike the pulling activity in the present study, the pressing activity was not performed to volitational failure. The experimental design in the present study was intended to be non-fatiguing with respect to BPT, thereby allowing participants to maximize power output over each of the 4 throws. Therefore, in the present study, it is perhaps not surprising that the BPT, TH, PV, and PP were maintained over the 3 sets, whereas BPOL, VL over 3 sets performed to failure was not. It would seem that the 4-minute RIs between like sets of non-fatigue ballistic exercises, whether interrupted or preceded by antagonist work, are sufficient to maintain power. Bench pull VL did not differ between the 2 conditions, but did decrease from set 1 to set 2. And from set 1 to set 3 under both conditions. This would seem to indicate that a 4-minute RI between BPOL sets performed to volitational fatigue was not adequate for the targeted musculature to recover and maintain VL. The results of their present study are limited to a single CS performed over 3 sets. Arguably, this is not indicative of resistance training sessions targeting multiple muscle groups. It is possible that the maintenance of power measures over the longer training sessions is not possible. It is also possible that the difference in sessions, VL, table 3, and the CS as compared with TS, although not statistically different in the present study, could continue to grow over a longer training session and become significant. Maintenance of similar acute TH, PV, PP, and VL under CS as compared with TS does not necessarily yield equivalent or efficient chronic development of strength and power. Practical applications. Time-constrained coaches and practitioners interested in training strength and power over the same time period, e.g. sessions, microcycle, or mesocycle, may be well advised to incorporate CS-type training. However, the use of antagonist preloading in an attempt to augment subsequent agonist power output is not recommended. Currently, the data supported by the hypothesis that CS-type training can enhance power output are limited. The study found that over 3 CS, there were no significant effects on BPT ability as a result of antagonist preloading. Similar maintenance of TH, PV, PP, and VL under CS as compared to TS indicates that similar stresses was imposed on the musculature in approximately half the time and suggests efficiency is enhanced under CS. Despite the inability to maintain BPOL, VL, BPT, performance measures were maintained under the CS condition, suggesting that strength and power training can be combined in a manner without compromising power output. Although similar under both the CS and TS condition, BPOL VL was not maintained over this session, suggesting that practitioners aiming to maintain VL may wish to implement RI of greater than 4 minutes when using heavy loads. Further research is required to determine the RI necessary to complete recovery when using heavy loads over multiple sets. Predictions as to CS efficiency or efficacy with respect to chronic adaptations would be speculative at this time. However, it is possible that CS training is an efficient and effective method in developing strength and power. Practitioners able to develop strength and power in a time-efficient manner will create more time for coaches to develop other components of performance. Conceivably, time-efficient development of strength and power will assist in enhanced athletic performance. Efficient development of strength and power will also have implications for the general population. Resistance training has been associated with improved health and decreased risk of chronic disease and disability. Arguably, resistance training programs offering results in less time may be more attractive to greater numbers of the general population. Before prescribing CS-type training to the general population, it is important to ensure familiarity with both high-intensity, e.g. 4M, and high-velocity, e.g. BPT, exercises. Increased numbers of individuals performing regular resistance training will have a positive effect on the overall health of a general population. Given this possibility, research investigating the chronic effects of CS training is warranted. Acknowledgements. This research was funded by the University of Ballarat, Australia. The authors would like to thank the University of Victoria, Canada, and Canadian Sport Centre Pacific for the allowance of laboratory space and equipment. The authors have no conflicts of interest that are directly relevant to the contents of this manuscript.